I wanted to spend a little bit of time talking about how you would practically scale a system. And by that, I mean, how large a battery do you need and how much solar panel do you need in order to provide sufficient energy to take care of what you need to take care of. So in this example, I'm going to say that you want to, that let's say it's dark for 16 hours or dark enough that you need to use floodlights to illuminate an area. That each floodlight takes 100 watts of power. And so you need to figure out how much energy you're going to consume during that 16 hours so that you can have a battery that's big enough to supply that amount of energy over that period of time. And so let's determine the minimum energy required for this, and then we'll go from there to figure out how many solar panels we'll need in order to make sure that the battery is full at the beginning of each evening period. So the first step is to determine the amount of energy that's required. So 10 100-watt floodlights means that you're consuming 10 times 100 or 1,000 watts, which is a kilowatt, and that you need to be able to provide that energy for 16 hours. So that's 16 kilowatt hours. And that's what I have here, I believe, on the next slide. Yeah. So that's how big the battery has to be in terms of its energy capacity. How much energy does it have to have? Has to be able to store at least 16 kilowatt hours. You would probably want to have a larger one just to make sure that you have some insurance in case batteries, sometimes their capacity goes down over time. And if you have a larger one, and means you can store more energy in case maybe some days the sun doesn't come out very much. You're depending on energy from previous days. So you have that little bit of extra in the battery. So that's to keep in mind, but the minimum is 16 kilowatt hours that you would need. Then from there, we want to figure out how many solar panels we'll need in order to charge the battery. And we're going to assume that we have 8 hours of sunlight. Now, I might have mentioned this in class. Sun doesn't just come on and then the solar panels are working 100%. The sun rises, and it's not until close to midday that the solar panels are producing as much as they can. And then it starts going down again towards the evening. We're just going to say that the sun has an average of about 1,000 watts per square meter when it's up. So I'm going to say we have, on the average, 8 hours of sunlight at 1,000 watts per square meter. If we're doing a really accurate solar analysis, we'd want to get more detailed than that, but we'll go with that for now. So the first step is to determine how many watts of solar panels we need in order to make this happen. And a watt is not an area, but we can convert a watt to an area later. So, we need 16 kilowatt hours of energy to be collected, at least that amount during the day. But we have 8 hours to do it. So 16 kilowatt hours divided by 8 hours is going to tell us how much power of solar cells we need in order to collect that much energy over that time period. So 16 kilowatt hours divided by 8 hours is 2 kilowatts. So our solar panels have to be rated at least at 2 kilowatts in order to make this happen. So now the question is, what area does that represent? Here's where we use something that you've already seen a little bit of. Here's where we use the fact that the sun has an intensity of about 1,000 watts per square meter. So that means that the solar panel, and also that the solar panels have an efficiency of only 20%, which means they really only collect 200 watts per square meter if the sun is shining at 1,000 watts per square meter. So given that, we now have enough information to determine the minimum area of solar panels that we need, and we can use the units to help guide us here. So I like to start by assuming the solar panels are 100% efficient, which they're not. So if they were 100% efficient and the sun is shining on them with 1,000 watts per square meter, then with 2 square meters of solar panels, we would get the amount of power needed from those solar panels in order to provide the energy we need over the 8-hour period that the sun is shining. So that would be 2 square meters. But now we have to take into account that the solar panels are not 100% efficient. They're only 20% efficient, which means they only collect a fifth of the sun's energy, which means we need 5 times as many solar panels than would be the case if they were 100% efficient. And we could get that by dividing the 2 square meters by 0.2. And that'll tell us that we need 5 times as many, or 10 square meters of solar panels. So we need a minimum of 10 square meters of solar panels to provide the energy required to charge the batteries over this period of time to supply the lights we need. And a rule of thumb actually is that often people double the minimum requirement, or at least increase it by some percentage to ensure that they have enough to get by over the time period that's of concern. Okay, I hope this helps you think about sizing solar panels. I have them on my roof. We did something like that based upon the amount of energy my household uses to try to get it pretty close to what we're consuming.